Okay guys, so in this video I'm going to run through about 20 questions to help you get ready for the final. So these are not in any particular order. So just remember that we're covering chapters 1, 2, 3, 4, 5 and 9 in this exam, and so you need to review the content of all of those chapters, and the final exam is going to be an approximately even distribution across all of those 6 chapters. So this begins relatively straightforward. It says complete each row of the table by filling in the missing prefix or missing exponent. So in the SI system of units, there are a whole series of prefixes and exponents, and the cool thing is that these are all listed out for you, so you just really have to look them up. So deci is equivalent as saying times 10 to the minus 1. So in this case, what's missing is the missing exponent. It needs to be 10 to the minus 1. 10 to the minus 6, that's equivalent to micro. So you just need to insert the micro symbol there. So that's just going to be 1 microgram for the second row. Centi is equivalent to times 10 to the minus 2. So the missing exponent on the third row is minus 2. And then finally, we've got 10 to the 6 as our power of 10, which is the same as mega, which is indicated with an uppercase M. Remember, milli is lowercase m and mega is uppercase M, and don't get the two confused. Okay, milli is equivalent to times 10 to the minus 3, and mega is equivalent to times 10 to the 6. All right. This looks like it's going to be a gas laws question. So it says an Arctic weather balloon is filled with 43.8 liters of helium gas inside a prep shed. So my initial volume is 43.8 liters. The temperature inside the shed is 13 degrees Celsius. So my initial temperature is 13 degrees Celsius, but we know we never work in Celsius. We always work in Kelvin, so we've got to add 273 to that. So that means that that's going to be 286.15 Kelvin. The balloon is then taken outside where the temperature is minus 18 degrees Celsius. So my change in temperature here, we're going to go from 13 to minus 18. So what do we get there? I'm going to do a calculator. This is my 7th hour of chemistry today, I think. So brain's a little slow. Go 255.15 Kelvin. We got it. All right. So I'm betting they're going to ask what is the new volume. There we go. Volume final. How many liters is that one? Okay, so we're changing from an initial state to a final state. And so we're going to use the combined gas law. P initial, V initial, Ni initial, Ti initial is equal to P final, V final, N final, T final. Now the amount of gas, it didn't change. The pressure didn't change. It's still just 1 atmosphere. So there we are. It's a Charles's law problem. So we want to solve for the final volume. So it's going to be V initial, T final on T initial equals V final. Plain old algebra. All right. Always write out your formulas with just symbols to begin with for a final exam. Always do your algebra before you insert any numbers, and then when you do insert your numbers, make sure you give units every single time. It's going to become critically important the further along you move in the chemistry sequence. Temperatures, we're always working in Kelvin. When we get to the end of our answer, we're going to check that it was logical. So the temperature went down, so we would expect the volume of the balloon to go down as well. So what happens? Volume final should be less than that 43.8 liters that we began with. So 43.8 liters times 255.15 Kelvin divide 286.15 Kelvin. And what do we get? 39.055 liters, because the kelvins cancel out leaves behind the liters. Now we're going to want to give this to 3 significant figures, so that's just going to end up being 39.1 liters. And there we go, 39.1 liters. Alright, so not too bad. Just double check everything. Correct number of Sig Figs. We got that. And liters, there it is in there. Okay, good. No problem. It says the pressure stays at exactly 1 atmosphere, so we were right with our pressure was being constant. It was the same amount trapped in the balloon, so the number of moles stayed constant. The only things that were changing were the volume and the temperature. Alright, let's have a look at this. A chemist measures the enthalpy change for the following reaction. Use this information to complete the table below. So if you see what's happened in the first one, in number 1, the reaction was reversed and then it was multiplied by 1/3. In the second reaction, what happened was that the reaction was just simply reversed. And in the third reaction, it looks like everything there was multiplied by 1/2. So we have the same direction, we just multiplied by 1/2. Now, we're asked to calculate the new enthalpy for these reactions, and we're going to give it to the nearest whole kilojoules per mole. And the key thing to remember is that when you reverse a reaction, you change the sign on the enthalpy. And when you multiply a reaction, you multiply the enthalpy. Okay, so in the first case, we have both of those things going on. So we have to change the sign from minus 320 to positive 320, and then we've got to multiply by 1/3 and then round to the nearest whole kilojoule. So 320 on 3, and that gives me 107 kilojoules. In number 2, all I did was reverse it, so I've just got to write that as 320, but remember to put the dot on the end so that that trailing 0 counts. And then finally, in the last one, I've just got to multiply it by 1/2, so 320 times 1/2 is going to be 160 kilojoules, and remember we need the dot on the end there. So that's pretty cool, right? We got that done fairly easily. Alright, 3 out of these 20 questions is done. Okay, so we're going to be writing the empirical formulas and naming ionic compounds. So remember, these are going to be systematic names, and they normally put in a couple that if you look up the common name, it will be different from the systematic name, so be aware of that. So in every case, we have a cation that has a +1 charge, and we have an anion that has a -1 charge. And so when the charges on your cation and anion are equal and opposite, you know that they're always going to combine 1 to 1. So in every case, the empirical formula is just going to have 1 cation with 1 anion, because these guys all have They both have the same size charge, right? They have the magnitude of the charge in each case is the same. So they just combine 1 to 1. Now the difficulty is the naming of them. So for cations, we've got to be aware of whether we need to put the charge in Roman numerals. And in this case we don't, because potassium is from group 1A, and anything from group 1A always forms a +1. So the cation in every case is just going to be potassium without the charge in Roman numerals. Now, the anion in each case here is a polyatomic anion. And it's an oxoanion, and it's that one of those where we've got like a family of 4, isn't it, right? So we know that the one with the most oxygens is going to be the periodate. That's going to be the IO4-. The one with 1 less will just be iodate. That's the IO3-. And then we will have iodite, That'll be the IO2 minus. And then we have hypoiodite, and that'll be the O minus. Now, hopefully you're wise enough to have a table of these polyatomic ions that you're going to look at. So this first one here, IO2 minus, that's going to be iodite. So this will be potassium iodite. The second one has 4 oxygens, so that will be periodate. The third one has 3 oxygens, so that's just going to be iodate. And then finally we have just the 1 oxygen, so that is going to be hypoiodite. Now you can always go to something like Wolfram alpha, and you can put this in potassium hypoiodite and see what it says. It might give you the formula, and there it is. Alright, and it gives you everything you could ever want to know about that. Now if I go just to potassium iodite, and there it is, potassium periodate, looking good. And I think the only one we didn't do was potassium iodate. And there they all are. So it all looks really good. So use a legitimate, like, you know, scientific search engine. And Wolfram Alpha is perhaps the best one because it was built by a chemist. And that'll help a lot when if you are going to like kind of like check stuff like that online. All right, looking pretty good. Moving on. It says acetylene gas is often used in welding torches because of the very high heat produced when it reacts with oxygen, producing carbon dioxide and water vapor. So I've got a hunch about this. It's either something to do with enthalpy of combustion, or alternatively it's to do with stoichiometry. Now, whenever you do a stoichiometry reaction, you're going to need a balanced, I'm already rushing ahead, let's not do that, a balanced chemical equation. So make sure you balance everything out nicely before you kind of, you know, before you get too far. So where are we at here? So 2 carbons, 2 carbons, 2 hydrogens, 2 hydrogens, 2 oxygens, and then we've got 5 oxygens. So that's going to need to be 5 on 2. And then we don't like that, so multiply everything by 2. So 2, 5, 4, and 2. And now let's check everything. Carbons 4 and 4, hydrogens 4 and 4, oxygens 5 times 2, 10. 4 times 2, 8, plus another 2, 10. So everything balances. Now we can get going with whatever the stoichiometry is that we're going to be asked to do. So please, please, please write out a balanced equation in your notes before you get going. Okay. Calculate the moles of acetylene needed. Okay. To produce 0.085 moles of carbon dioxide. So it's simply a moles of A to moles of B, where that's my A and that's my B. And how do I do moles to moles? I use a mole ratio. So 0.085 mole of carbon dioxide multiplied by, and according to my balanced equation, I need 2 moles of acetylene for every 4 moles of CO2. Cancel my units. I got to halve that amount. All right. So now Sig Figs, we're going to be going out to 2 significant figures because we were given 0.085 has 2 significant figures. So 0.085 times 2 on 4, and that gives me 0.0 4 to 5 mole of C2H2, which to two significant figures with 0.043 mole of C2H2. And that's my final answer. So really, I am looking for your work to look something like what I've got here. Balanced equation, correct math, with including all of the units, and then the units being cancelled. And, you know, it shouldn't be an issue. All right, it should look like, you know, you've just taken a quarter of chemistry and not like you don't care about what you're doing. All right. Oh, this looks like an enthalpy question, or at least a heat question. The units here look like we're going to be solving for heat capacity. A chemist carefully measures the amount of heat needed to raise the temperature of a 148 milligram sample. So this is giving me my mass, isn't it, in milligrams. So that's the same as 0.1480 grams of sample. And we're going to change the temperature from 46.3 up to 67.6. So delta T is always T final minus T initial. So in this case, we're going from 67.6, or we're going up to 67.6 from 46.3, and that's going to be in Kelvin or Celsius, however you want to describe it, because remember, a change in degrees Celsius is the same as the change in Kelvin units. Okay, so that's my change in temperature, and then it says the experiment shows that 13.2 joules of heat are needed. So Q equals 13.2 joules. Okay, that's all my variables. What can the chemist report for the specific heat of the capacity? Be sure your answer has the correct number of significant figures. So 4 Sig Figs for that guy, 3 Sig Figs for that guy, 3 Sig Figs for that one. So we're going to be 3 Sig Figs. So our little formula is Q equals MC delta T. We're solving for specific heat, so it's going to be Q on M delta T equals C. And now we're good to go. 13.2 joules divided by 0.148 grams times 21.3 Kelvin. There we go. All right, so now what do we end up with? Joules, grams, Kelvin. And we want this to 3 significant figures. So 13.2 divide, don't forget to put the bottom line in parentheses, 0.148 times 21.3, enter, and it ends up being 4.19 joules per gram per degree Kelvin. Now another way of writing those symbols for those units that are on the bottom line there would be to give them a -1 as the exponent. So there's your answer there. Looks great. Okay. All right. And so again, it should look, it doesn't have to be perfectly neat, just like mine isn't, but you can follow my reasoning there clear as day. All right. Here we go. This one here is that one about the whole interconversion between potential energy and kinetic energy. So a few things to keep in mind is that there's no change in the total amount of energy, right? Okay, so what happens is they begin with a lot of potential energy, and as that goes down, the kinetic energy goes up, and then so that's what's going to be happening when you're rolling downhill. And then when you're rolling uphill, the kinetic energy is going down, but the potential energy is going up. So the cyclist is stopped at the entrance to a valley, and so they have 0 kinetic energy, but they are above the ground, they're above the floor of the valley, so they have some potential energy. In fact, that potential energy, you know, is all they have. They have 100% potential energy at point A and 0% kinetic energy, all right? So it says, where would the cyclist have the highest potential energy? Now, if they kind of, you know, actually pedaled, the highest point above the ground there would be F. They couldn't roll to F because the highest they can roll is to E. But if they pedaled a little further, they could get up to F. So F is where they would have the highest potential energy. They would have the lowest potential energy at the very bottom of the valley there, so at D. And where they have the lowest potential energy is where they have the highest kinetic energy, because as the potential energy goes down, it gets converted into kinetic energy. So they're going to be going the fastest at the bottom of the valley. And so that answers the next question, where would they have the highest speed? Well, they have the highest speed where they have the greatest kinetic energy, so that is at D. And then it says, would the cyclist kinetic energy be higher at A or D? Well, they have 0 kinetic energy at A, so it has to be higher at D. And then it says, would the cyclist potential energy be higher at A or D? Well, they're a lot lower at D than they are at A, so it would be highest at A. And then it says, would the cyclist's total energy be higher at A or D? And the energy doesn't change. It just gets turned into kinetic energy from potential energy. So the answer to that is not applicable, or whatever the option is. And then it says, suppose the cyclist lets off the brakes and coasts down into the valley without pedaling. Even if there is no friction or air resistance to slow him down, what is the furthest point the cyclist could reach? And it would have to be here, right? Because, they can't have more energy than what they begin with. So they're going to end up just at a point where they have exactly the same energy as what they started with. So here they would have 0 kinetic energy and 100% potential energy, but they can't get up to F just by rolling. Okay, so that's that. Those are pretty straightforward. You've seen those a couple of times now, so theoretically that you should be familiar with it and not really struggling too much. Just be careful not to make a dumb mistake. All right. Rank the samples of gas described in the table below in order of increasing average speed of the atoms or molecules in them. So, the thing to keep in mind is that the root mean square speed, right, is just equal to 3RT on M. So there's some things that do affect the speed of the particles. The temperature affects the speed of the particles, and as the temperature goes up, the speed of the particles go up. The molar mass affects the speed of the particles, and as the molar mass goes up, if the temperature is the same, then the speed will actually go down. Things that don't affect the speed of the particles: the pressure, the volume, and the amount. Okay, so those things are irrelevant. So we're just focusing on the molar mass and the temperature. And in particular, the one with the smallest mass and the highest temperature is going to be going the fastest. So we have slowest, and we have the fastest. The fastest ones are going to have high T and low mass, and the slowest ones are going to have a low T and big mass. So that's how we're going to characterize these. So when I look here, we've got 2 types of particles, right? So the amounts are irrelevant. I'm going to forget about that. And the pressure is irrelevant, so we're going to forget about that. And we're just focusing on the 2 things, the mass and the temperature. So what we see is we have 2 masses. We have krypton and we have neon. And krypton, if you look in the periodic table, is right at the bottom of group 8A, and neon is right at the top. So what we're really saying is krypton is heavier than neon. Okay, so krypton is bigger. So our big mass and things are going to be krypton. Now, what's our lowest temperature there? Our lowest temperature there, we've got 3 temperatures. We've got minus 101, we've got 91, minus 91, and we've got minus 81. So that's it. There are 3 temperatures, right? So what thing here has the lowest temperature and the biggest mass? Krypton. So that is the krypton is at minus 101 is going to be going the slowest, right? Because nothing else is at minus 101. So we want to put 1 next to the molecules that have the slowest average speed. So that guy has got to be 1 because it is the heaviest particles with the lowest temperature. Okay, so then now we've got 2 that are at 91, right? But the heavier ones are going to be going slower. So krypton at minus 91 is going to be number 2, right? It's going to be the next slowest. And then we've got 2 samples of neon left. One is at 91, minus 91, and the other one is at minus 81. So the one that's at the lower temperature, because they have the same mass, is going to be going slowest. So that's going to be number 3. And then finally, we've only got 1 left over, and that is the lightest gas at the highest temperature. So it's got to be going the fastest, all right? So check it. Do we have the slowest one? Should be the lowest temperature with the biggest mass. We've got krypton at minus 101, so that was correct. And then the fastest should be the highest temperature with the lowest mass, and that would be neon at minus 81. So we've at least got the 2 endpoints right. And then the 2 that are in the middle, they're both at the same temperature, so that means that the heavier one should be going slower. And that's what we've got, because we've got krypton rated as going slower than neon. So it looks like we got it, we nailed it. All right, moving right along. Liquid hexane will react with gaseous O2 to produce carbon dioxide and gaseous water. Okay, so it's looking like a stoichiometry calculation, so we want a balanced equation. So I'm just going to write this out in a more conventional form. So it's C6H14 reacting with O2 to form, you guessed it, CO2 and water. Classic combustion reaction. Just doing a quick balance. Going to need 6 carbons, 7 waters, and then we're going to have an issue with the oxygens as always. 6 times 2 is 12, plus 7, that's 19. So that'll be 19 on 2, and then doubling everything. And that should be about right. So let's see what we've got. So carbons, 2 times 6 is 12. 12. Hydrogens, 2 times 14 is 28. 14 times 2 is 28. Oxygens, 19 times 2 is going to be 38. And then over here, 12 times 2 is 24. Plus another 14. 38. Okay, so that's cool. That all balances. Now, if I look at here, I look at this, I can't divide through by a common multiple, so I've got the smallest whole number set of coefficients. Just want to make sure that I collected my carbons and hydrogens correctly for hexane. 1 plus 4, that's 5. 6 carbons, which I've got. And then 4 times 2 is 8. Plus 3 is 11. Plus another 3 is 14, so that looks good. So that's my balanced equation. All right, on with the rest of it. Suppose 58.6 grams of hexane is mixed with 83 grams of O2. Calculate the minimum mass of hexane that could be left over. Okay, so what we're really trying to do here is identify what is the limiting reactant, and if hexane is the limiting reactant, there will be 0 grams of hexane left over, and if oxygen is the limiting reactant, there will be 0 grams of oxygen left over, but some hexane. So the first thing we've got to do is figure out what is the limiting reactant, and how we're going to do that is by doing 2 grams to grams calculations. So we're going to do 1 for hexane and 1 for O2. So 58.6 grams of hexane times 1 mole of hexane, and let me just do this, 6 times 12.01 plus 14 times 1.01. You can use an online calculator if you want. I'm just kind of trying to keep things simple, 86.2 grams of hexane. Now we need our mole ratio. I get 12 mole of CO2 for every 2 mole of hexane. And we may as well go through to grams because our final answer is going to be in grams. 44.01 grams of CO2 per 1 mole of CO2. And there we go, 2 grams to grams calculations. First one's almost done. Yep, we got it. The only thing left over is grams of CO2. So we'll go through, and it looks like we're going to be to 3 significant figures for this. So 58.6 times 1 on 86.2 times 12 on 2 times 44.01, and so it ends up being 179.51. 179.51 grams. So if all of the hexane were able to react, that is how much carbon dioxide we could produce. Now we're going to do our second grams to grams. So we got 83 grams of O2. 1 mole of O2 is 32.00 grams of O2. And then according to our balanced equation, we get 12 mole of CO2 for every 19 mole of O2. And then finally, our molar mass, 44.01 grams of CO2 per 1 mole of CO2. So, second grams to grams calculation, let's just check our units. It's real easy to get something upside down. So 83 times 1 on 32 times 12 on 19 times 44.01. What do you got? 72.095. 72.095 grams of CO2. So what that's telling you is that your oxygen is your limiting reactant, right? Your oxygen is your limiting reactant, and then once you made your 72 grams of CO2, you're out of oxygen, and so some hexane will be left over. So oxygen is your limiting reactant. So how many grams of hexane can we consume? And that's what we've got to work out now. So grams of hexane consumed. It's pretty simple. We got 83 grams of O2. In 1 mole of O2, there are 32.00 grams of O2. And according to our balanced equation, we use 2 moles of hexane for every 19 moles of O2. And finally, we know that hexane has a molar mass of 86.2 grams. So we're going to use up 86.2 grams of hexane for every mole of hexane that we consume. So let's see what we've got here. Grams of O2, moles of O2, moles of O2, moles of hexane, leaves me with grams of hexane. So this is grams of hexane that gets used up. So let's see what we get. 83 times 1 on 32 times 2 on 19 times 86.2. And so I'm going to use up 235. Oh, sorry. Woo. Did a dodgy conversion from scientific notation. I'm going to use up 23.535 grams of hexane. So that's how much gets used, right? Used. Didn't really leave enough space there, did I? Okay, so that's how much going to get used. How much did we start with? We started with 58.6. So what remains? 58.6, what we started with. How much got used? 23.535. That's what got used. What's left over is how much remains. Start with 12 eggs, you use 4, you'd have 8 left over. 58.6 minus that, 35.5 35.1. 35.1 grams. All right, and that's it. Now, it's kind of a little, how do we round all of this off? Well, we knew our O2 to the gram, to 2 sig figs. So we would have rounded this off at 2 sig figs, which would have left us at 23, or actually would have left us at 24. So we would give this to the ones, all right? Because 58.6 to the 0.1s, and then we'd be subtracting to the 1. So we'd give that to the ones. So yeah, so that would end up being 35 grams to the ones, all right? Now, there's not any advice about that, I don't think, in the question. Be sure your answer has the correct sig figs, yeah. So 35 grams. All right. A gas made up of homonuclear diatomic molecules, so it's something like this, X2, escapes through a pinhole 1.62 times as fast as krypton. Okay, so it escapes through a pinhole faster than krypton. So what this is really saying is it's a Graham's law problem. Now it says write the chemical formula, so basically we want to know what X is. So what we know is that the rate of X2 escaping divided by the rate of krypton escaping is equal to 1.62. But we also know, according to Graham's law, that that's going to be equal to the square root of the molar mass of krypton divided by the molar mass of X2. So we want to solve for the molar mass of X2, don't we? Now, we could put it into an online solver, or we could just use math. So squaring both sides, and then multiplying both sides by that, and then reorganizing, and so the molar mass of X2 would be the mass of krypton divided by 1.62 all squared. There we go. So then we would need to look up the molar mass of krypton, which is pretty easy to do. I'm just going to go into here because it's kind of a all in one place to do that. There we go. And there's the mass, 83.798 divided by 1.62 squared. Now it should be lighter because it's escaping from the pinhole faster. So the molar mass for this diatomic, 83.798, divide 1.62 squared, and that ends up being 31.93 grams per mole. Now that's for a diatomic gas, so the mass of X is just going to be 31.93 on 2. So that's going to be very close to 16, isn't it? 15.965 grams per mole. So what do you think X is? What element has a molar mass of approximately 16? X is oxygen. All right. So our homonuclear diatomic material must be O2. So O2 leaks out of a pinhole quicker than krypton does. There you go. So if you wanted to prevent gas from leaking out of a container, you'd use krypton over O2 because it would leak out slower. All right, 1.6 times slower. Jacinto Sweets sells jars of jelly beans in various sizes. Decide whether each property of their jelly bean jars listed in the table below is extensive or intensive. Okay, there were ones like this that were about pizza, right, before. So extensive depend on size or / amount, I think is a better way of saying. All right. Intensive don't depend on amount. So that's it. So an intensive property could be the mass, and an extensive property would be the mass, and an intensive property would be temperature. All right. The number of yellow jelly beans in the jar. Each property of the jelly bean jars listed in the table below. So if you had a bigger jar, you would have more yellow ones, right? You'd have more of everything. So if you had a bigger jar, you would have more yellow ones. So that means that it is extensive. Okay. The probability that a yellow jelly bean lies right next to a black jelly bean. Well, that's not going to depend on the size of the jar. That's determined by like the ratio of the different colors in the mix, right? So if you had a big jar or a small jar, it's going to be the same probability in that one. So that one is an intensive property. There would only be like one case where I can consider that you could take this to the extreme, and if you had a tiny jar that could only fit one jelly bean in it, then there was zero probability of a yellow jelly bean lying right next to a black jelly bean, but that's not what they mean. Okay, the percentage of jelly beans in the jar that are yellow. Again, that's kind of like the ratio. That's kind of like the ratio of the black ones to the yellow ones. It doesn't matter on the size of the jar. The percentage, the distribution of the colors is the same. So that is intensive. All right, that's an interesting one. I like that more than the pizza one. Okay, let's have a look. Oh, it's looking like... Oh, it looks like a really easy pressure conversion problem. So the gas pressure inside an ordinary vacuum chamber is 0.000658 atmospheres. Oh, that looks like a recipe for trouble. I'm going to rewrite that in scientific notation just so there's no errors. Calculate the gas pressure in millimeters of mercury and torr. So it's pretty easy. 1 atmosphere is equal to 76 millimeters of mercury, but it's also equal to 76 torr. So what we're really saying is that however many millimeters of mercury this is, it's the same number of torr. So it looks like you have to do 2 conversions, but you actually only have to do 1. So 6.58 by 10 to the minus 4 ATM times, and then we need ATM on the bottom, don't we? And millimeters of mercury on the top. And that's it. So you just got to multiply that number by 760. ATM cancels out, leaves me with millimeters of mercury. We actually have space to put it on there. It says give your answer to 3 significant digits. So 6.58 by 10 to the minus 4 times 760, and it ends up being 0.5001. 0.500. And that's it. That's 3 Sig Figs. All right, okay. And you know, you can do the math if you want, but hopefully you'll come to the same conclusion. Here we go. Okay, 3 Sig Figs. So remember, trailing zeros count if there's a decimal, but leading zeros never count. Okay, looking good. Question number 13. Let's see what it is. Okay, writing a balanced half reaction. And it's an oxidation. So remember, oxidation is loss. That means electrons are products because the reactants are losing electrons. Of solid gold. So gold is not a diatomic element. And you're going to go to aqueous gold 3 cations. So AU, AQ, 3 plus. All right, so we have to balance for charge, right? And So how do we balance fixed charge? We balance fixed charge by adding electrons to the more positive side. So total charge here on the left is 0. Total charge on the right is 3 plus. 3 plus is more positive than 0. So I've got to add in 3 electrons, and then the total charge becomes 0. So that's easy going. All right, just don't make a mistake. All right, just, take your time and get it done. All right. Oh, this looks like some kind of applied stoichiometry problem, doesn't it? An aluminum atom has a mass of 4.48 by 10 to the minus 23 grams. So that feels like they're just giving you a conversion factor, right? 4.48 times 10 to the minus 23 grams of aluminum for every 1 atom of aluminum. And a small airplane has a mass of 5,000 kilograms. So 5,000 kilograms, or we can say 5,000 by 10 to the 3 grams. Okay. Use this information to answer the question below. Be sure your answers have the correct number of Sig Figs. Well, that guy there is 3 Sig Figs, and that one there is 4. So let's see what we get. What is the mass of 1 mole of aluminum atoms? Well, that's really easy actually, isn't it? So you have to use the information that was given, all right? So we want the grams in a mole, okay? So what I know is that 6.022 by 10 to the 23 aluminum atoms are present in 1 mole of aluminum atoms. And I know that 1 aluminum atom weighs 4.48 by 10 to the 23 grams. So you can see here aluminum atoms cancel out, and this will give me grams of aluminum per mole of aluminum atoms. Alright, and so let's see what we get. 6.022 by 10 to the 23 times 4.48 by 10 to the minus 23 ends up being 26.98. Now it says give to the correct Sig Figs, so we only used one piece of information there, which was from this 4.48 by 10 to the minus 23. Avogadro's is a constant, so it's 26.9786, but we've got to round it off to 3 Sig Figs, so it's going to end up being 27.0 grams of aluminum for every 1 mole of aluminum. So there we go, 27 grams in a mole. And if you look that up on the periodic table is in chapter 2 of your book, or you can do the old look up aluminum in Wolfram Alpha, and you'll see there it is, 26.98, which is what I got when I went out to the full out here. You see when I went out to 4 Sig Figs, so that's perfect. All right. Naming acids. So all of these guys, with the exception of this one, are an oxoacid, and then HCl is a binary acid. So you'll have 2 sets of naming rules, one for binary acids, which is the most complicated, and then the other one for the oxo or oxy acids, however you want to say it. So you could look the rules up in the book if you want. So for binary acids, these are ones that when you take the acid, it makes an anion that ends in IDE. So in this case, it makes the chloride anion. And when you name those, you name them as follows. You go hydro, the stem name of the anion, which in this case will be chlor, ic, and then acid. Now for the oxoacids, we actually have two rules. So I should point out that this one here, HCl, is just going to be hydrochloric acid. For the oxoacids, we have two rules. If you take the acid, when you dissolve it, it's going to form either an ite or it's going to form either an ate. And the ites become us acids and the ates become ic acids. So the real big drama is making sure that you understand what the anion is, right? Now the charge on the anion is just equal to the number of hydrogen ions, hydrogen atoms that are present in the formula of the acid. So I know that this one's going to be Cl2 minus. I know the next one will be SO4 2 minus because there's two hydrogen atoms, and then I know the last one will be BrO3 minus. So this guy here is called chlorite. This one here is called sulfate. And that one there is called bromate. So a couple of things that you're probably going to want is you want to go to your book, and then if you go to chapter 3, chapter 2 right at the end, there's chemical nomenclature, and one of the sections in here, I think it's the last section, it has rules for binary acids, and then it has rules for oxyacids, and it has a bunch of examples. The only one that's going to be relevant for us in here is going to be this guy here, sulfate, and you can see you could pull sulfuric acid out of there. So, you know, you don't have to know this, you just have to know how to use the rules, right? You have to know how to recognize an oxyacid and a binary acid. All right, so what do we know? That the ates become ic acids and the ites become us acids. So HClO2 contains the chlorite anion, so it is going to be called chlorous acid. Right, H2SO4 contains the sulfate anion, so it's going to become sulfuric acid, right? Because the ates become ics. And then finally we've got the bromate, so it's going to become a bromic acid. And we can double check all of these things to make sure that we've got them right if we have enough time. So let's have a look. Bromic acid, BrHO3. So it's given them in a different order, but that is HBrO3, right? And what did we have? HBrO3. Okay, so that's cool. We kind of know this one, don't we? Because it was in the table. H2SO4, there you go, right? Sulfuric acid, so we've got that one correct. Okay, and then we want HClO3. It's going to give us the name. No, it didn't give us the name. Oh, well, this one is called chlor. And it gives it in a slightly different order, but it's still HClO3. So we know we got it right. Okay, so we have a little bit of time to kind of to check that. Oh, chlorous acid. Sorry, because it was HClO2, wasn't it? Yes. Chlorous acid. Here. There we go. Chlorous acid. HClO2. Perfect. All right, so there we go. That's fine. Oh, it looks like it's a heat problem, but this time we're going to be solving for a temperature or a change in temperature. Okay, let's have a look. A 29 gram sample of glass, so that's giving me my mass, which has a specific heat capacity of, okay, so 0.670 joules per gram per degree Celsius, is dropped into an insulated container containing water. Okay, all right. Okay, and so the water is at 30 degrees Celsius. So we've got two parts to this. So we've got 300 grams of water over here. Okay, we know that the heat capacity of water is 4.184 joules per gram per degree Celsius. At 30 degrees Celsius and a constant pressure of 1 atmosphere, the initial temperature of the glass is 82. So T of this guy is 82 degrees Celsius. And T initial of this one is 30 degrees Celsius. Okay, so if you're going to put these two things together, you know what's going to happen, right? The temperature of the water is going to go up and the temperature of the glass is going to go down. Right? So that's what's going to happen, and it's going to stop changing when they're at the same temperature. So that they're going to have the same final temperature, and we know that T final will be greater than 30, but it'll be less than 82. So we kind of know where it's got to be going here. It says assuming no heat or okay. Calculate the equilibrium temperature, which is the final temperature of the water. Be sure your answer has the correct number of Sig Figs. Okay, so everything up there has either 3 or 4 significant figures. We'll keep an eye on that as we go through though. So what we know is that the glass is going to lose heat, and the amount of heat that will be lost will be mc delta T. And so we know that what's going to be lost is equal to 29 grams times 0.670 joules per gram per degree Celsius. And then the change in temperature we don't actually know, but it's always T final, which we don't know, minus T initial, which we do know, and that'll be in degrees Celsius. Okay, so that is how much is lost. Right? Now, the amount of heat that is gained is going to be the mass of the water times the heat capacity of the water times the change in temperature of the water. And what we know is that heat gained is equal and opposite to heat lost. So the heat that was lost is equal and opposite to what was gained. Alright? So what was lost was the 29 grams times 0.670 joules per gram per degree Celsius times T final minus 82 degrees Celsius, and that is equal to minus the mass of the water, 300 grams, times the heat capacity of the water, 4.184 joules per gram per degree Celsius, times the change in temperature of the water, which is T final minus T initial degrees Celsius. So what I'm going to do now is I could either evaluate for all of that and solve for the T final, or I could put it into an online solver, which is exactly what I'm going to do. I'm going to put that into an online solver. So I'm going to make sure that I copy it over correctly. Don't want to be making any errors there. Alright, so I got that down. So then I'm going to hop on over to my favorite Wolfram Alpha. And instead of putting formulas in, I'm going to be putting in math. Alright. And I'm just going to put what I'm trying to solve for in as x. Now, I'll know whether I've got this correct or not because it should be more than 30 and less than 82. So that's always a good thing to know. All right, so I think I got that in there okay. Hit enter. And it comes out as 30.7927. There we go. All right. So just make sure that I definitely got everything correct. The original temperature was 30, 82. Yeah, that all looks good. All right. So Online Solver tells me that my temperature final should be 30.7927 degrees Celsius. And now I've just got to decide about my significant figures, right? So I had my... Okay, so on the left here, everything was going to have 3 Sig Figs. And on the right here, my mass, I think, had 4 Sig Figs. Yeah, it did. This guy had 4 Sig Figs. This was going to be out to 3 Sig Figs. So that's also going to be 3 Sig Figs over there because of the delta T was going to be 3 Sig Figs. So that means that my answer should have 3 Sig Figs. So my final, it's going to be 30.8 degrees Celsius. So it doesn't go up by much. All right, doesn't go up by much. But when you think about it, we are dropping in a relatively small piece of glass, right? You know, it is kind of hot, but it's pretty small. So I'm happy with that. All right, let's have a look at this one. Oh, it looks like a concentration, but it's got weird units because it's micromoles per liter. A chemist prepares a solution of calcium sulfate. So calcium sulfate, we know that if you're going to dissolve that in water, you would get calcium ions and sulfate ions. By measuring 0.56 micromoles of calcium sulfate into a 400 milliliter flask and filling it to the mark. Calculate the concentration in micromoles per liter. Oh, this is kind of easy. We've just got to turn that into liters, haven't we? 400 milliliters times 10 to the minus 3 liters per 1 milliliter. There we go. So that means that we have 0.400 liters because we've got to go out to 3 Sig Figs. And so then we want micromoles per liter. So it's going to be 0.56 micromoles divided by, oh, that's me, 0.400 liters. And so ultimately this is going to be out to 2 Sig Figs, isn't it? Right? So we've got to get the right number of Sig Figs here. So 0.56 on 0.4, and so that ended up being 1.4, and we want it to be 2 Sig Figs because this guy is 2 Sig Figs. Okay, good. Looking impressive. Happy. Question number 17. Study this chemical reaction. That means pay attention to what's going on. Magnesium plus iodine. Magnesium is a metal. Plus I2, non-metal, forms Mg I2. Oh dear. What kind of compound is MgI2? It's an ionic compound. Okay, what do metals do when they act with nonmetals? They get oxidized. They get oxidized and they form cations, right? So what's going to happen is this. Electrons go that way, right? Like that. So the magnesium, what kind of cation is it going to form? Well, you have to look at the ionic compound, don't you? Magnesium's in group 2A, so it always forms magnesium 2+. And then iodine is in group 7A, So it always forms I-. So that makes sense because they combine in a 1:2 ratio. So this is going to form Mg2+. And to get it to balance, you're going to have to add in 2 electrons. You can see that the magnesium is losing 2 electrons. This is oxidation because oxidation is loss. The nonmetal, I2, becomes 2 I-. And how is it going to do that? By gaining the 2 electrons that are lost by the metal. So that is reduction. There we go. Okay, so we're up to question 19 of this set of practice problems. So it says the vapor pressure of methanol at 25 degrees Celsius is 126 torr. Calculate the vapor pressure in millimeters of mercury and atm. Round each of your answers to 3 significant figures. So all it's really saying is take 126 torr and turn it into atm, and then take 126 torr and turn it into millimeters of mercury. So it's a pretty straightforward kind of process. We just have to recognize that 1 atm is equal to 760 torr, and then also recognize that 1 millimeter of mercury is equal to 1 torr. So let's just keep it simple, huh? However many torr it is, it's exactly the same number of millimeters of mercury, so it is 126 millimeters of mercury. This is already at 3 significant figures, so I'm happy with that. So now that just leaves the one conversion to do, which is the torr into atm. So 126 torr times 1 atm is 760 torr. Torr cancels, and there we go. So 126 divided by 760. And that ends up being, to 3 significant figures, 0.166 atm. So there we go. There are our 2 answers. All right, last but not least. Okay. Oh, this looks like it could be a Boyle's law question. A cylinder is filled with 10 liters of gas. So our initial volume is 10 liters. Now I'm calling it initial volume because I'm imagining whenever they're talking about a piston and a cylinder, I'm thinking that a change is going to occur. And a piston is put into it, so it's capped. The initial pressure of the gas is measured to be 159 kilopascals. So pressure initial 159 kilopascals. Okay. And then it says the piston is now pulled up, expanding the gas. So volume final, don't quite know what it's, and we do know what it's going to be. It's going to be 72 liters. And it says calculate the final pressure of the gas. So that's what we're after. Be sure your answer has the correct number of significant figures. So everything here looks like it's got 3 Sig Figs. So gas laws we're only ever doing multiplication and division, so my answer should have 3 Sig Figs. All right, so I'm changing from an initial state to a final state, so I'm going to use combined gas laws. So P initial, V initial is equal to number of moles initial, T initial, and that's P final. V final is the number of moles final, T final. The number of moles doesn't count because it's trapped behind a cylinder, a piston, and the temperature isn't changing either. So it's just going to be like that. We're trying to calculate for P final. So PI VI on VF gives me PF. And that's it. So PI was 159 kilopascals. VI was 10 liters, V final was 70.2 liters. Everything has 3 Sig Figs, so it expanded. The pressure should go down if a gas expands. Let's see what we've got here. 159 times 10 divided 72 ends up being 22.1 kilopascals. Total sense. The volume went up by about a factor of 7, and the pressure went down by a factor of 7. 3 Sig Figs all the way through. Everything looks good. All right, guys, that wasn't a all of the possible types of questions that could be assigned, but it was a decent number of problems. I did 2 per week, which is similar to the number that you're going to get on the final exam. That took me, with explanation, about an hour 10. So, you should have no trouble getting through 25 questions or so in the time that's allotted to you. So I think that was good. It doesn't cover everything, but it's a good start to help you with your revision. So good luck with everything, and please, please, please make sure to show your work in a neat and tidy fashion, and in particular write out your formulas with no numbers in them, first of all, just using symbols, and then secondly, always make sure you include all of your units so that I can see what you're doing, and then finally, make sure you cancel your units, because that's going to increase the probability that you're going to detect any errors that you make. All right, so, and also when you cancel your units, have a look and take seriously what's left behind. And if they don't cancel out in the way that you're expecting, then you can guarantee that you got the problem wrong, and if you have time, you should go back and rethink about it. All right, okay, good luck with everything, and catch you around.